here. It's good to see you all, you guys. Otherwise, you all look like ghost students. So it will be good to feeling teaching to real person.
Maybe at the beginning for a second just to figure out how this is gonna work. I'm planning on just like writing down what he said.
Hi everyone. So it's good to see you. If you want, we can start. So I'm muting you all. So if you have questions, you can post on the chat. I guess you can unmute yourself if you have a question, right? Just not to have any background noise, so it will be better. Okay, we can get started. So when someone asks question about how many questions we will have a question on the exam. Actually, if you go to the introduction or the instruction about the exam, you will see we have 18 questions with 4 points and 4 questions with 7 points. So we will have 22 questions, less than the exam 2. So okay, the goal of this session is I will review chapter 25, 26, 27, and 29, and important parts, not all the parts. And so I will solve some problems straightforwardly for some chapters and do some introduction for some. If you need any clarification, just please stop me and I can go beyond the reasoning of how I start the problem, like solve solution that way. So I would like to cover everything. That's why like I'm skipping some parts. So otherwise we need to stay here all night. Okay, so first part is about Snell's law. So these are the typical problems you may see on the exam. So in the first problem, actually it was on the discussion problems of chapter 25, 26. So ask the rank the indices of refraction for the material. So you start with the Snell's law. Let's say you have NA sine theta A equals NB sine theta B. When you are entering from a medium with low index of refraction, let's say 1, and if you are going let's put this here, Na1 and Na2, you have a larger multiplier next to the angle so that the sine theta B will be smaller compared to sine theta A. So that when you are entering a denser medium, which means that larger refractive index, the angle is gonna be smaller. So when you compare the incoming incident light, the refracted light is gonna be closer to the normal, which is this line, normal to the surface. So which means that NB is larger than NA. And when you look at the second figure, the light, the ray gets further away from the normal. So when you try to do this, the theta C, you see is larger than incident angle. So which means that the NA is larger than NC. So then if you rank all of them, NB is larger than NA, NA is larger than NC. So that's how you approach and solve this problem. For the second one, you have I'm going on this fiber problem. A light ray enters the end of the fiber, the surface of which is perpendicular to its side, which means it's a cylindrical. If N1 is 1, and N2 is 1.44, what's the minimum value of theta 3 for total internal reflection? If we look at the normal, what's the criteria for internal reflection? So let's say you have N1 sine. So if you look, I mean, the in total internal reflection happens when you have a light originated at the denser medium and it's trying to enter a lighter medium. But when we look at this N1 sine theta and 2 sine theta 3, let's say it doesn't reflect and it want to go to this way, okay? Let's say theta 4. So N1 1, so sine theta 4, and you have N2 sine theta 3. So let's assume it's not total internal reflection. And what would happen when you have a refraction from medium N2 to the first one? So that theta 4 is the hypothetical case. But what you see is the left-hand side is a sine function and cannot be larger than 1. Because the maximum value of the sine function is 1 and it happens at 90 degrees. So which means that when the theta 4 is 90, then after that, everything is going to be internal reflection as you increase the theta 3. So what we will do, sine 90 for theta 4 will be N2 and sine theta 3. So sine 90 is 1, and I put the N2 at the bottom, the denominator, and you have sine theta 3. Then you have 1 over 1.44. So which is 1.44. It's going to be 0.694. Okay. So, but we are not done yet. We need to find the value of angle. Right now, we found the sine of that angle. So what you need to do is to use an inverse sine function. So if you haven't used it, it's a trigonometric function. You have to use your calculator. So, but I mean, one thing you must be careful if the calculator is set for the radian or the degrees. So, for example, if I open a calculator, so you see functions here like sine and inverse sine. So for example, if you know the sine 30 is 0.5, right? So sine 30 is going to be, so let's say degree, but I choose the degree. I didn't do it at the beginning. So that let's say, oops. Second. 30. So maybe, okay, now it's radian, I guess. Oops. I'm really bad at this calculator. So, okay, sine 30 is 0.5. This is how I check if every calculator is different. So then I use inverse sine function, which is this one. So inverse sine, and let's try for 0.5, should give the 30. So that's how it gives it 30 degrees. So this is how you can check if the calculator works properly. Like it works, but the setting is proper. So what we need to do is we need to put this sine 0.694, right? And if you remember, we are trying to find the angle which has a sine 0.694, and I make equal. It's 43.9 is like a 44 degrees.
So we want our calculator in degree mode?
Yes. If the question asks specifically radian, then you can switch to radian, but I will not do it. I will ask always degrees. So theta 3 is 43.9. So if the question asks you to round, it's gonna be 44 degrees. Okay. So for the third problem, I have a transparent cylinder radius with 2 meters. So this is 2 meters. Let me make it smaller. And the light ray travel in the air, incident, and the reflex from the mirror, and exit being parallel to the incoming light, incident light, and the distance is 2 meters between these two. So this problem actually is a trigonometry problem. We will use the physics at the end. So this is also radius, and it's 2 meters. And the distance between two rays is 2, so which means that the half is going to be 1 meter and 1 meter. So then to determine the reflection index of refraction, I need to find this angle and this angle, right? Theta 1 and theta 2. So then I can use the Snell's law to find the refractive index of the medium or glass. So then what you see is here, this distance is 1 meter, and this is 2 meter radius. Then I can find this angle. That actually, the sine of that angle, I call it alpha, is gonna be 1/2, right? The opposite divided by the hypotenuse. That sine alpha equals 1/2. And from trigonometry, you will see this angle, this triangle is has equal, it's too big. This angle has theta 2 here as well because of having the same sides. Then the alpha will be, and then if you think this angle, we can call it beta, and theta 2 plus beta will be 180 degrees, which is the total angles of a triangle. And you see that alpha plus beta is also 180 degrees. Then you can see that theta 2 plus theta 2 equals alpha, and the theta 2 is half of the alpha. Okay, from this sine alpha being half, if you use inverse sine function, you will find that alpha is going to be 30 degrees, right? Then theta 2 is going to be 15 degrees, and theta 1, which comes from being the parallel, so you have this parallel alpha, and it will be exactly the same for the theta 1. So this is gonna be theta 2 as well, like, and 30 degrees. Then you know the Snell's law, sine theta 1 times 1, because the 1 is the index of refraction of the Ayer. And we have n times sine theta 2. So when you plug it, sine 30 equals n times sine 15. I need to draw this line. Okay, then n will be sine 30 divided by sine 15. So on the calculator, if you use, oops. Okay, you ask how did you know the alpha? Let me just find this from the calculator. I like this calculator better. Sine 30 degrees, okay, divided by sine 15 degrees. Okay, it's gonna be 1.93. And it's gonna be 1.93. So we can do this. It's gonna be the answer for the refractive index. Okay, the question says, how did you know the alpha equal to theta 1? So when you have two parallel lights or rays, when you have a line crossing them like this, so that this angle will be identical to that angle. So if this is theta, or I can call it alpha, this will be also alpha, right? Because these lines are parallel. So then if you look at this, this is a central line and the parallel to this line, the incident ray. So these are parallel. So that the alpha will be equal to theta 1. So this is the normal, like it's a perpendicular to the surface. This goes through the center of the cylinder. Okay.
Professor, can you clarify why n equals sine 30 over sine 15?
So here I use a Snell's law, like on this part. So I know that theta 1 it's alpha, and I know that theta 2 is 15 degrees. Theta 1 is 30 degrees, and theta 2 is 15 degrees. So then I can use the Snell's law, which says N1 times sine theta 1 equals N2 sine theta 2. N1 is 1 because it's air, and sine theta 1 is sine 30, that's incident angle, equals N, which is I'm looking for, and sine 15. Okay. So again, this is a trigonometry problem. Like you need to find those triangles. They are very like isotriangles, like they have the same edges, same angles. And alpha makes 2 theta 2. So after that is just Snell's law. But until that point, like it's a trigonometry problem. It's not an easy one, I guess. Okay. So then we learn about the nearsightedness and farsightedness. In the nearsightedness, your eye works harder, which means it focuses more than it should. Then what it makes is the focusing power is stronger. So it focuses the images very close to itself, like to lens, instead of back of the eyes. So to correct this, we use diverging lens, which means it's diverging instead of focusing, it's defocusing. So this is defocus. So it's kind of reducing the power of your eye. Okay, on the other hand, in the farsightedness, you can see the far away, which in which your eye doesn't work too much. But in farsightedness, you cannot see the near. So which means it happens usually when you are old. So it means that your eye is losing its focusing power. So to correct that, you use converging lens to increase the focusing power of your eye. Okay, does it make sense? And the question typically look like this. So when you are young, the minimum distance your eye can focus is 20 centimeters. As you get older, your eyes start to focus objects only at 60 centimeters. So you cannot, you lose the focusing power, so you can only focus at 20 centimeters. What is the focal length of the lens you need to use to be able to see the object at 20 centimeters again? So it means that it's farsighted. We will use the converging lens. So focus it here. So you have an eye and you have a lens here. And your eye can see things at 60 centimeters very well. But the question says, if you put an object at 20 centimeters, how you can see it, which means that you need to increase the focal power of your lens or eye. You will use a converging lens. So that converging lens is going to create that object image at 60 centimeters. Okay, So it will create that image of object at 60 centimeters. So then you will be able to see it. Does it make sense? Because your eye can see right now, when it's on the 60 centimeters. But that converging lens helps to have the image at 60 centimeters when the object has 20 centimeters. So we will use a lens equation, 1 over S1, it means S object, plus 1 over S image equals 1 over F. So the one thing you must be careful here, the image is gonna be virtual, and because of being the same side of the lens. So when you have an image on the other side of the lens, then the location will be positive. But this is about the sign convention. So if the image is at the same side, so it must be negative, which means that 1 over S object is 1 over 20 centimeters plus 1 over minus 60 centimeters, 1 over F. So, and then if you do this, like you make the denominator same, so you multiply by 3, it will be 3 over 60 centimeters minus 1 over 60 equals 1 over F. 3 minus 1 divided by 60 equals 1 over F. Then F is going to be 60 divided by 2 equals 30 centimeters. That will be the focal length of the lens. And it's a positive, which makes it converging lens. So it's like a double check. And when you go to the doctor, it's you talk about the diopter, it's gonna be 1 over F in terms of meters. So the question asks about what's the focal length. It doesn't ask the diopter, so you don't have to convert that focal length to the diopter. Wait, what happened to the 20 centimeters? It's here. So it's here, like, that's the location of object plus 1 over S image, location of image equals 1 over F. So 1 over 20 plus 1 over minus 60 equals 1 over F. Why it's 60 negative? Because the image is virtual and it's on the same side of the object. So that's why the image has the negative 60. So if you want in terms of diopter, we will make this 1 over F equals 1 over 0.3 meters and 3.3. So yeah, the sign convention is the most difficult part of these lenses. So when like in lecture 25, right? Is it this one? I think it's about lecture 2. So when you and we learn about the location of the object at different position. So, and the one we looked at this one. So this is the where we see how we made the location negative. So, for example, if in the question we saw, we do from inverse, like it gives the location of the object and the image, then we find the focal length. That in here, in this example, we walk through by knowing the location of the object and the focal length. Then you see the location of the image was negative, -3f. So that's like the why you have a negative sign on image. So if you go to this chapter 25, lecture 2, you can see by yourself. If you have any question, like we can see again. Like, okay. So I'm moving another question. A person has a near point of 50 centimeter and a far point of 400 centimeter. Which lens can correct his far point to infinity? So what's happening here, you have an eye, and the lens, it can focus well between 50 centimeter and 400 centimeter, right? So then what we need to do is we need to make a trick by putting a lens, and what it's gonna make is that when you have an object at infinity, it will put at 400 centimeter. Lens will put in the object at infinity to 400 centimeter. So you have an object at infinity, then it will put to 400 centimeter at 400 centimeter. So this is nearsighted. So you see the near, but you cannot see the far. So we will use diverging lens. Also, you can look at how you can form such configuration when you have an infinite the object and where will be the image. So you can do this only with the diverging lens. So if when you put a diverging lens in front of the eye, so what's going to happen is when you have a 1 over s object, 1 over s image equals 1 over f. So the s object is going to be 1 over infinity, and 1 over image is going to be 1 over minus 400 centimeters. So equals 1 over f. Again, the object and image at the same side, so that's why I put this 400 centimeters. In the sign convention, to be able to have both positive, they must be in the different sides. Then the focal length is going to be minus 400, because this is going to be in 0. 1 over infinity is 0. So that's with that you can correct the far side, like the far point of that patient. Okay. And we have another question. An intersection of a hospital hallways, a convex spherical mirror is mounted high on the wall to help people to avoid collisions. Like when in some trucks, also like to be able to see large areas, use convex lenses. So it forms a smaller virtual image behind the mirror. So the magnitude of the mirror's radius curvature is 0.4. What's the magnification of the image of a patient located 10 meters away? So you have a convex mirror, okay? Then it says that the radius is 0.4. Then the focal length is going to be half of the radius, 0.2 meters, right? Then when you have an object at 10 meters away, let's first find the location of the image. 1 over S object plus 1 over S image equals 1 over F. And here, when the S object is 1 over 10 meters, and I'm looking 1 over SI, and 1 over F is going to be negative because it's a convex mirror. The focal length is behind the mirror, so that's why like it's the negative. It's going to 1 over 0.2. Then what's going to happen? 1 over SI equals 1 over 2 minus 1 over 10, right? Then SI is going to be 0.2 times 10 and minus 10.2. So it's going to be 2 divided by 10.2 equals 1 over minus 9.6, right? And that's the location. So it's going to be somewhere here, image. Then the magnification is going to minus location of image divided by location of object. So location of image is minus 196 divided by 10, and it's going to be 0.0196. So it's about like 2% of the object. Okay. Okay, now we have two more questions about chapter 25 and 26. And it's about magnifying glass and a telescope. Oh, maybe 3 more. Okay, 3 more. Okay, in the next question, a person uses a converging lens of focal length 4 centimeters as a magnifying glass. What's the maximum possible magnification? So the near point distance is 25 centimeters. So you have, we already given this formula. So the magnification will be near point divided by focal length of the lens, or when you use your lens to focus more, you can increase the magnification a little bit. It's gonna be n over f plus 1. So it's just use this formula, and the maximum means we need to use the second one. It's gonna be 25 divided by 4 plus 1. So it's going to be 7.25. So how we derive this, like if you are interested, I can go over, but for the sake of time, I can just use it. Okay, the next question, for an object in front of a diverging lens, image is always virtual and in front of the lens. So is it true or false? Actually, if you go to the lecture notes, so we find this location of the image So to find the location of image, you send lights from an object, right? So first you send from the tip of this object and goes that way. Then what you do is you can go to send the second light from the center of the lens, and will go straight without any refraction. So what's happening here, that because of property of diverging lens, the lights are diverging, they don't intersect. So if they don't intersect, they don't form a real image, but they have projection of the light, so you can see, it can form an image by projection of the rays. So the projection of rays is gonna be here. Then you will have an image at here. So in other words, like if you try to do math, so this, to find the location of image, so the focal length is always negative for the diverging lens, and minus SO. So from this, you also see that the SI is going to be always negative on the same side of the object, and it's going to be smaller and virtual. Virtual means that it's not a real image. So in the real image, you have real light intersect. In the virtual, the projections intersect. So from this, you see it's a true. For the next one, you have available lenses of focal length 2, 4, 8, and 16, and you're trying to build a telescope. So what's the maximum magnification you could achieve? So the magnification is proportional with the ratio of the objective focal length and eyepiece. So in other words, you need to try this, make maximum. So the maximum focal length is 16 centimeters. So you need to use that. And for eyepiece, you need to use the minimum to make it maximum magnification. From this, you will have largest magnification is 8. So here it's asked the absolute value. So that's why I ignore the minus. To reach the maximum, so I can delete this. The number just means that it's inverted. So maximum magnification is going to be 8. It's proportional, the ratio of F objective and the eyepiece. Okay, so that's all for chapter 25 and 26. In 27, we talk about diffractions. So we have 4 questions from chapter 27. The first question is about there's a spy satellite at height 180 kilometers and uses 500 nanometers. So it's a Rayleigh criteria to find the resolution. So when you have a camera up back there in the satellite, so you're trying to distinguish 2 points, let's say A and B. So these are gonna form some diffraction, okay, or some circular aperture diffraction. So the criteria is when you see these peaks separate on your CCD camera, let's say, now you can distinguish. If you see the like a combined like blurb diffraction pattern, that means you cannot distinguish 2 points. So the 1.22 comes from this the circular aperture calculation. So under this theta minimum is given 1.22 lambda divided by d. So that it only depends on the diameter of the lens and the wavelength of the light. That theta is gonna be equal to this theta. From this, you can use some small angle approximation. So this, let's say small d over the height is gonna be sine theta. And if you use small approximation, then you can make this theta, sine theta equals theta. Then it will be equal to 1.22 lambda over d. So then it asked what would be the minimum diameter of the lens. So it asked the capital D. Then let me put this here, D over H equals 1 over 1.22 lambda divided by capital T, D, and then that's what I'm looking for. And to solve for D, you put like cross products. Let me do this way, D times D equals 1.22 lambda times H. Then the capital D is going to 1.22 lambda times H divided by small d, right? And if you plug in the numbers, 0.22, the lambda is the wavelength of the light, and I assume it's 500 nanometers. It's like a green-white light. Okay, I will put 10 to the minus 9 meters. Then the H is 180 kilometers. So it's kind of 180,000 meters, and divided by small d. Small d is 1 meter. From this, capital D is going to be what? Actually, I did this calculation. 1.22 times 500 times 180, and it's going to be 0.1098 meters. So that's the diameter of the lens you need to use. Okay, the next question about thin films. Now you have thin film of soap coated the piece flat of glass. How thick is the film if the reflects 581 nanometers light more strongly when illuminated with normal white light? So what happens is, because of interference, the some of the light will be destructively interfere and some will be constructively interfere. Yes, I will post these recordings later on. So if you have to leave, feel free. But it's better to stay if you have any questions. Okay, so when you have thin films, so let's say it's a soap and you have the glass. So you send a bunch of light, but what you see is the 581 nanometer reflects strongly. So which means that the waves will constructively interfere, which means that they will have the same phase. So think as a wave, so it goes this way. So and the second wave, then and you add them, right? So like if I use this space for this demonstration, so you have one wave. So this is like a two wavelength. So this is one wavelength, and this is the second wavelength. And imagine I am having another wave. I'm just doing the same phase. So again, this is lambda corresponding here and 2 lambda corresponding here. Okay, now when you add these waves, they will constructively interfere. And what you see is when you shift this wave by lambda in either way, like plus or minus lambda, they will be the same, right? The wave is gonna look exactly the same, and then they will have a constructive interference again. So what you need to do is the path difference between this top reflecting and the bottom side reflecting waves have only lambda wavelength. So this is constructive interference. So you have a thickness. So the bottom wave has 2 theta thickness. When it reflects back, it propagates 2 times of the thickness because it reflects it and comes back. So does this motion or path will be equal to the lambda. But the thing is that lambda is going to be smaller in that medium compared to the air. So, and then you need to use the 1.43. It says that that's the medium light travels. Okay. One says, how do you know when to use small approximation of theta? So you can use a small approximation when it's you can play with like the radian, sine, some theta will be theta. So usually less than 5 degrees. So you can do that trick. Okay, let's go back this question. 3. So like that 2 thickness is gonna be lambda, but lambda is different in that SOAP medium. Then what you have is thickness equals lambda divided by 2 times 143. Lambda is 581 nanometers, right? And divided by 2 times 143. 581 divided by 2 times 1. So it's going to be 203 nanometers. Why did you use and not? Because this is top one is the SOAP and the bottom one is glass. The glass is thick, but the SOAP is thin, just a very thin layer. There is no back reflection from the glass. What kind of reflection you see is first from the SOAP interface, from this interface, and the second, the interface between SOAP and glass. So you see these lights coming to you after they reflect. So that's why like the light travels in the SOAP. That's why I use 1.43. Okay. And for the next problem, we have diffraction grating experiment or 2-slit experiment. The separation is 18 micron, or we put in this way. Here, and find that the second bright line on the screen is formed at angle. Okay, you pass this 2-slit experiment, and the second bright peak, this is 0th order, 1st order, and 2nd order. And you have -1 and -2 as well. So this is gonna be d sine theta equals m lambda. The m is these orders. So then basically it asks what's the wavelength. So d sine theta, you can convert to meters. Sine 5 equals m lambda, is m is 2 second order, second bright line, and lambda. So you solve for lambda, it's going to be, I will do 18 10 to minus 6 sine 5 divided by 2. So then what I have is here sine 5 degrees whose point, and then I multiply with 18 and divide by 2, and 784. And I have 0.784 10 to minus 6 meters. So to convert to nanometer, it's going to be 784 nanometers 10 to minus 9. Why did you use to m for m? Because it says the second bright line. So you have the first order in here, the 0th order, and you have the first order and the second order. So maybe you are you asking the, I mean, this, why don't you count the 0th order as a first line? Actually, that's a good question. So, yeah, the question is not very clear on that, but I assume it m equals 2 as a second order. But it says, if it says a second order, it's gonna be clearer. Because 0th order, that happens at the center. You have first, and the second order, m is 0. So the two lines or two paths have the same path. Two rays have the same path. So there's no path difference between them, and that doesn't have any the phase difference. So when you have a 0 phase difference, they constructively interfere and it forms the 0th order. So in the question, it will let us to what order. Okay, yeah. In the question, it should give that number. But yeah, and other than that, like it's just straightforward to use this d sine theta equals m lambda equation. Okay. What angle is needed between the direction of polarized light and the axis of a polarizing filter to reduce its intensity by 66%? So what's happening here, you have polarized light. Let's say I assume it's a vertical polarized light. And the polarizer axis is making an angle, let's say called theta. And if you're sending some intensity, let's say I, the transmitted intensity is gonna be I times cosine squared theta. That's a polarized light. And the output polarizer is gonna be the same as the polarizer. So, but it says the intensity is reduced by 66%. So which means that the transmitted light is 34%. So I times 0.34, right? Then cosine squared theta is 34. Then cosine theta is square root of 34. Then how would you do this? Go to then you need to do inverse cosine and do the square root of 34. Then it's giving the radian. Then you need to convert into degrees, and it's gonna be 54 degrees. The blank PowerPoint is already on Canvas. Yeah, okay. So this is how you can find the theta. So what I did is cosine inverse 54. So where did you get 34%? Because it says the reduce the intensity by 66%. So which means that the remaining is 34%. Yeah, I did right? Like, Michaela, does it make sense? I assume your silence, yes, okay. So the trick is this, like when you have a polarized light, then to find the intensity of the the transmitted light, you will just multiply with cosine square theta. And if you have an unpolarized light, this is not asking the question, don't get confused, but as a side information, when you have a unpolarized light, like from sun, when it enters the polarizer, it loses half of its intensity. That's a side note. Okay, next question. When a photon enters into medium with different refractive index, which one of the photon changes? It's wavelength, frequency, or both frequency and wavelength. Any idea? A, yes, that's correct. Its frequency is constant because its energy is constant. You don't want to, because the energy of photon is proportional with the frequency. So it's a kind of makes sense. Frequency doesn't change, but speed changes. So wavelength changes. An electron is accelerated through a potential difference of 400 volt. What is its wavelength? So what would you do is, like, you have an electron, you give some kinetic energy by this potential. So then that's potential, the kinetic energy means it has a momentum. And then you use the Broglie wavelength relation to find the wavelength. So that potential energy turns into kinetic energy. And then the wavelength is given by this momentum. So E times V, that's the potential you are giving, and equals 1/2 mv squared, right? And from this, we can solve for V 2 times E times V divided by M. Then to find the wavelength is like using when you have a light, it's it's similar to how you do that with the light. Like it's a wave property of the material. Of the material, like that's the wave and particle duality problem or the concept. So you divide h by the momentum. That's h is the Planck constant. For the velocity, you can use E times V divided by M. So this will be like calculating and doing some algebra, but you need to find a couple of constants. E is electron charge, 1.6 10 to minus 19 coulomb. The mass of electron is 9.1 10 to minus 31 kilogram. Then Planck constant is going to be 6.6 10 to the minus 34 constant. So you will be giving in the exam, yes, 6.6 10 to minus 34 joules second. So then I know I can do it, but I don't have calculator with me. It will take some time. So if you guys are fine, I can skip this part. You will just plug in the calculator. So can you always set 1 electron volt to kinetic energy? So Emila asked, what does that mean? So it's about units. So electron volt is always energy. And for example, when you have an electron accelerated in 1 volt, it gives 1 electron volt energy. So yes, they are the same. So I can simplify. If you put M inside, one of them is gonna cancel. It's mass of electron. So it's okay, I can move on because I don't have like the handy calculator. I have to plug in a Mathematica if you want. Okay, let's do it. I don't know. It's gonna run quickly. I will new document. It's gonna be 6.6 10 to the minus 34. We have square root of 2 times electron volt 6 10 to the minus 19 times 400 volt times M is going to be 9.1 10 to the 10 to minus 31. So it looks like lambda is 6.1 10 to the minus 11 meters. Okay. So next question, we don't have much. Millikan's oil drop experiment determined what? Any guess? Electron charge, mass, or mass charge ratio? Not the mass. This is charge. If in the experiment, what it did is it suspended oil drops on the electric field where you have mg equals QE equality. From this, he found, like from this, he determined the size by he looked at it with the microscope. He determined the size of the droplet, which depends on the sprayer, and then found the mass, and he knows the electric field, he knows the potential is giving between two plates. And he was always finding the integer number multiple of the electron charge when you find all the Q's. What happens is, like, when during the spray, some droplets uses one or multiple, like integer number of multiple electron charges, electrons, let's say, so that he was able to find the electron charge. Okay, we have this concept, Compton scattering. That's an experiment confirmed the particle property of the electromagnetic wave and as an X-ray. So before, I mean, the electromagnetic wave is assumed as an electromagnetic wave, not a particle property. But these photoelectric effect, Compton experiment, Rutherford experiment, these all confirm the particle property of the photon. And what happens is, like, when you send the light, it collides with electron, and the photon reflects. So during this time, the photon gives some energy to electron. So if the energy of the photon decreases, the wavelength increases, right? And then the collide electron gains momentum because it starts to move, right? So this is kind of what you need to remember. Then we have this black body radiation, and that's also important point to start to understand quantum physics. In the previously, before quantum physics, all the theoretical calculations suggesting this black body radiation curve like this. This is pre-quantum era. So then what you have is this UV catastrophe. How to say the I need to help from Google. Okay, it says, sorry guys. So which means that in the theoretical calculation, it says that you must have a lot of UV light, but which is not the case. Like when you in the universe, you don't see that. Like otherwise we couldn't survive. So which suggests that the energy in the universe has some quantized property and proportional to the temperatures. So that helped to develop this black body radiation. And when we did some experiment with sun and others, like the stuff, like we heat the metals, we measure the surface, and we measure the radiated spectrum. We understood this physics. So that's what you need to know about black body radiation. And we have 3 more questions about the photoelectric effect. In photoelectric effect, Einstein sent a light on a plate, and the electrons are kicked out, and they come to the positive side of this plate. Everything was under the vacuum, like a glass tube. So the electrons are kicked out. What he did is he changed the potential. Like instead of like making that positive, he made this negative and positive. So what happens, like he could stop the electrons before reaching the left side. So that's, we call it stopping potential, which means the electron kinetic energy equal the stopping potential. Oops. Okay. So this experiment is important because it allows us to understand the particle theory of the light. So these are some observation and explanation. And in the problems, what we typically ask is, when light of wavelength 350 nanometer is incident on a metal surface, the stopping potential of photoelectron is 0.5 electron volt. What's the maximum kinetic energy of the electron? So actually what we just said is true for this. Like stopping potential equals the maximum kinetic energy of electron, because the electron has an initial kinetic energy when it leaves this right-hand side, but whenever it consumes all the potential energy to overcome this potential, it stops there and comes back. So there is no current passing through between 2 plates. So it's gonna be 0.5 electron volt maximum kinetic energy. For the second problem, you have 2 40 nanometer photons hits on a surface, and the maximum kinetic energy is 2.48. What's the work function? So we will use this equation. The photon has energy. The sum of it consumes by the work function, and remaining is gonna be the kinetic energy. So what you have is 2.48 equals HF is the energy of photon minus work function. So how we find the photon of energy? So you know the wavelength, 240 nanometers. So you know the wavelength, you can find the frequency, and the HF is going to be energy. So frequency is going to be C over lambda, right? The inverse of the period, lambda over C is the period, and inverse is C over lambda. Then that's going to give the energy in terms of joule. Then you need to convert into electron volt, or you can use H as the electron volt unit, but let's do that like here. Okay. So you H multiply with C, it's going to be 3 times 10 to the 8 divided by 240 nanometers minus 9. Then it's gonna give you in terms of joule. And if you divide by 101.6, 10 to the minus 9, it should give the in terms of electron volt. So this is giving 5.15 electron volt. So do you have any trouble with this calculation? So I can share that screen if you want. Okay, so let me write down here as well if you have some question. The energy is gonna given by 6.6 10 to minus 34 times 3 10 to the minus 10 to the 8 is the speed of light. The wavelength is going to be 240 10 to the minus 9, and you divide by the 1.6 10 to the minus 19 to convert into electron volt. So that gives this 5.15. Then you have this electron volt. Let me write down. Then the phi is gonna be 515 minus 248. And 5.15 minus 2.48 is going to be 267 electron volt. That's the work function of the material. And the last question, the kinetic energy of photoelectron depends on which of following. So Einstein showed that it doesn't depend on the intensity, it's independent of the intensity. And duration of illumination, it doesn't matter, but it depends on the wavelength of the light, right? Because it depends on the frequency, and nature, it depends on the wavelength of the light. So then the answer is gonna be C. Okay. So that's all. So it's quite late. I think my wife is calling. So we have to stop here. And if you have any question, just we can do another one, and just feel free to email. So I will post this as soon as possible. Okay.
Thank you.
Thank you all.